Synchrotron X-ray tomography is the only technique that allows non-destructive 3D imaging. By measuring the interaction of X-rays that pass through a sample, we can measure its geometrical and relative density, both externally and internally. In this tutorial video, we will explain the basics of X-ray tomography. Through an attenuation contrast by experiment, first we will place our sample on a stage. Then the X-ray beam will penetrate the sample as it rotates. Then the attenuated transmitted beam is converted to visible light by using a scintillator. This visible light is optically magnified through multiple microscope lenses. This will be reflected on a mirror to project and record the resulting imaging on a CCD detector. Images are taken at each fixed angle of the rotation, which provides information about the total absorption of the sample in that particular orientation. This set of projections, which are usually more than 1,000, are fed into a tomographic reconstruction algorithm that provides a tomogram. Because attenuation coefficients are different for each phase of the sample, the internal structure of the sample is therefore visible. The monochromatic X-ray causes a photoelectric effect involving inner shell ionization. An electron from the K-shell will be ejected if the X-ray energy is higher. Then, the vacancy left will be filled out by an electron from the outer shell L. Here, the destabilization of the atom is corrected by the release of photons and electrons. Now, let's move forward to the reconstruction. Reconstruction is done through the Fourier slice theorem. A parallel X-ray beam penetrates the sample in the xy plane in a direction given by S with an attenuation coefficient distribution μxy in real space. The projection is acquired at the incident angle theta. Then, as the beam passes through the sample, the X-ray intensity will drop exponentially according to the Beer-Lambert law. At every position along C, which is orthogonal to the beam propagation, projections will be given through a two-dimensional Fourier transform represented by the colored map here, and a one-dimensional Fourier transform represented by the red graph. Polar coordinates are used in this Fourier slice theorem. Now let's move forward to the results. Here we can see an image of lithium represented by dark gray and electrolyte by light gray. After attenuation contrast and phase contrast, we can obtain the line profiles across a lithium electrolyte lithium interface. Attenuation causes a decrease in beam intensity, which reflects to the imaginary parts of the complex refractive index. Refraction causes a deflection of the beam, which refers to the real part of the complex refractive index. Then the final image is obtained, and here we can see the lithium electrodeposited structure in 3 dimensions. Also, X-ray tomography can be used to look at the expansion volume of lithium upon lithiation. Thank you so much for watching this tutorial.